All right, so last time just to review a couple of slides here, we were talking about two kinds of programming languages, interpreted languages versus compiled languages. All right, I think we looked at Hello World in assembly language for Linux, right, last time. So we kind of saw what at the end of the day, what a low-level language looks like. So that's from this slide. There's three kinds of languages: machine language, zeros and ones, not for us. A low-level language like we looked at last time, where we were actually looking at a power tool because we were leveraging the operating system for doing a lot of the heavy lifting for us. And then lastly, a high-level language, which has a one-to-many relationship with the CPU, and that's what we like. We like to write one or two lines of code and have it translate into a whole bunch of stuff on the CPU. Okay, and some examples of our high-level languages are languages that we've probably heard of. All right, Python, Java, C++, yada, yada, yada. All right, we talked about the nature of the CPU last time. We were doing all those little hand exercises, stuff like that. So CPU is a collection of magic tricks that when, this doesn't look all that impressive, but when we, take that movement together with 50 other movements in a certain order, we can do some fairly impressive things like shoot a basketball, pick up a cup of coffee, things like that. All right, so a CPU is kind of like that, where it has a whole bunch of little tiny abilities that maybe aren't all that impressive in and of themselves. But when you put them together in a very specific order, something real gets accomplished. All right, so then this is where we looked at Hello World in Python versus Hello World in assembly. We talked about two kinds of programming languages: interpreted languages and compiled languages. Interpreted languages being relatively slow. We say relatively because computers are really, 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 really fast. And these guys require something called an interpreter, versus compiled languages, which are relatively fast. These guys require something called a compiler. All right, so we talked about what is an interpreter and what is a compiler. So an interpreter is a computer program that you feed a high-level language into, and in real time, while the program is running, it translates it into code that the computer can understand. So somewhere in there, it's going to translate into a low-level language that then ultimately gets translated into zeros and ones that ultimately get processed by the CPU. A compiler does that work, but it does it before you ever run the program. Okay. And then summarize, you could say interpreted languages, this runs at runtime, where a compiled language happens prior to runtime. So to be specific, what does a compiler do? This translates a high-level language into a low-level language, specifically before we run the program. And you only need to do this once per modification of the code. So every single time you make a change to your program, you need to recompile it to give you a new executable that will then run directly on the hardware. All right. But when you go and get a video game or something like that and you install it on your computer, you're not the one programming that game. It was programmed back at the company somewhere. You don't have to recompile it each time. Go ahead.
How long does it actually take to compile?
Well, it depends. So for programs that we might write in here, kind of relatively small programs, let's just call it instantaneous. If you are one of those, like last time I showed you a Linux program, and I kind of encouraged you that if you're, want to be a little geeky and get your own Linux set up, going, the most user-friendly Linux is probably a distribution called Ubuntu. But then you have some versions of Linux, like another one's called Gentoo, that you can actually compile your own Linux operating system. And sometimes it can take 3 or 4 hours to compile that because it's compiling 10,000 programs that all need to be linked together and stuff like that. So it just really depends on the size, complexity of the application. All right. But generally speaking, for things that you might work on in your normal career path, when you compile something, it's very quick. It's doing that heavy lifting. The writing of that compiler is the part that's very difficult. All right, that's why we see so many interpreted languages come out today and very few new compiled languages. And we'll talk more about that as we kind of jump into things. Now here's kind of a picture representation if we have a high-level programming language, whether that is Python or something like C++. Both of those would be high-level languages. Difference is Python's an interpreted language, C++ is a compiled language. All right, so both of those guys are high-level languages, though. They go through the necessary converter. So either a compiler that happens before runtime or an interpreter that's happening at runtime. And ultimately, that high-level code that we as humans like writing gets translated into a low-level equivalent that maybe we wouldn't want to write, but we could if if our life depended on it. And then ultimately, that gets translated into a bunch of zeros and ones, which we would never want to do by ourselves. And then it runs on the computer. Make sense? All right, so the process is kind of the same. The difference is what happens between the high-level language that we write and ultimately that low-level zeros and ones kind of combo that happens right before it runs on the CPU. What's the tool that's in the middle that makes our life easier? Is it a compiler or is it an interpreter? All right. We did mention last time, I think we asked the question, it was kind of right at the beginning, right at the end of class, like when would we still use assembly code today? Like when would a human being actually go down to this low-level example here and actually write some of that code? So let's say a modern-day video game is written in C++. It's probably, call it 90% of modern video games are written in C++. Maybe we're starting to make a transition over to C# or something sometimes, but let's just say it's C++, which is a compiled language. So, you write the whole video game in this high-level language. You use a compiler to compile, to translate that high-level C++ code into low-level assembly code for Intel. Now, let's say there's a certain part of the game that needs to be really, 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 really fast. And that high-level language, because of the rules associated with programming, it has to be completely unambiguous, happen to force you to write some code that you happen to know as the human being who's solving this problem will never get executed. But the code would not compile unless you put that alternative option in there, because the programming language itself doesn't know that if this if fails, that this else won't occur, even though you might know as a human that you're never going to get into that secondary else statement. So what you can then do is you can go into the produced low-level code from the compiler and modify that a little bit so that that question doesn't actually get asked. Speeds things up a little bit in certain situations. Probably a fairly rare circumstance. You'd only want to do that in a part of a game that is really suffering from performance. Some scene that has tons and tons and tons of explosions where, one little extra question being asked might be the difference between, a reasonable frame rate and something that looks kind of choppy, that kind of thing. But it's going to be a fairly rare occurrence today. On top of that, we also have to consider the quality of the compiler. So this tool right here, this compiler that sits between the high-level language and our low-level language, we're at the mercy. When we write our C++ code, there isn't just one correct solution to a problem. Okay, human beings were professional problem solvers, and especially from a beginning programmer perspective, when you start writing code, many of you are going to come up with some pretty strange solutions to problems that maybe happen to work. And maybe that solution to the problem actually makes sense to you. All right? Now, when you see me solve it in class, it might be very different than the way you solved it, but it ultimately comes up to the same result. Now, maybe while you should ultimately aspire to having maybe a more efficient solution to a problem, don't just artificially try to write super efficient solutions to a problem at the cost of you not really understanding what you're writing. I'd rather you have correct solutions that you understand that just happen to be inefficient, leveraging how fast our computers are, because who cares? Let's call it 98% of the time, if a really, really efficient solution to a common problem versus the most inefficient solution to the same problem is going to run instantaneously on a modern computer. Our machines are really fast. So don't go out of your way to try to write really, really, really efficient code or, measure the quality of your program by how many lines of code it took. Be verbose. Write it in such a way that makes sense to you. over the years, you'll start making it a little bit more condensed or a little bit more concise or more efficient, things like that. Write code that you understand. All right, but understand that one of the jobs of a compiler, we can kind of go back here, we can say that a compiler, one of its jobs is to make a bad programmer look better. Okay, so you might write some really crappy, but technically, functionally correct high-level code. You just go about it in just a bad way. All right? And a very modern compiler might make some of your garbage translate into more efficient low-level code than it should. All right, so we can say that compilers have gotten smarter over the years. But a compiler is a computer program that human beings had to write. All right, and compilers are very, very, very difficult to write. One of our upper division classes, we look at compilers like in CSC200 systems programming. These are not easy tools to write, and even writing them at the easiest level isn't going to produce the most efficient low-level code. So you can imagine over the years, like the C++ compiler, which is, there's a GNU one called G++ or GCC, and then there's the official Unix one, CC or C, then a plus after it. Those guys have evolved over the last like 60 years, all right, to the point where they're producing fairly optimized code now. And maybe each year when the new version comes out, it's getting some fraction of a % better. But in year one, when that compiler first came out, it was probably producing pretty sketchy code that just happened to work. Make sense? All right, so compilers are really difficult to write, so that's why you don't see a lot of new programming languages come out that are compiled. That doesn't mean that they don't exist. You tend to see interpreted languages come out 3 per day. In general, if you really dive into the language of the world of new programming languages, only some of them make the CNET newsfeed or something like that. But you know, everybody and their brother in computing is coming up with some sort of interpreted language for solving some very specific problem that they happen to be working on. You know, they're making a Dungeons and Dragons role-playing game or something like that, and they just write a language that is the language of D20 or something like that, and that's fine. Makes their life easier, so you kind of create a power tool. That's no different than when you're, at home working on a project, and you can do something one time, or you can kind of create some kind of weird duct tape / screwdriver monstrosity that you can use for each additional time to solve that specific problem, right? All right, so that's just kind of human nature. But interpreters are much, much easier to write. They're written in a high-level language. They are just translating from one high-level language really maybe into another high-level language. So nothing keeps you from maybe writing an interpreter for your new made-up D20 language, let's say. And that interpreter actually just converts your D20 language into the equivalent Python. And then you use your traditional Python interpreter to run your code. So you're just giving yourself a little middleman there to let you write stuff in a certain way, and then it turns it into normal human speech. Okay? So interpreters are kind of a dime a dozen. Go ahead.
Does writing your own code like that slow down the interpreting?
Oh, well, I mean, the answer is yes. The more filters something has to go through, it will get slower. But then again, we come back to the thing where our computers are really, really fast. So it's going to have to take certain types of problems where you're going to even notice the difference. I mean, we're not going to feel the difference between a program running in 3 nanoseconds versus 8 nanoseconds, right? Even though technically it was almost 3 times slower. Make sense? Yeah, so one of the jobs of a compiler is to make a bad programmer maybe look better, and typically compiled languages are really, really, really focused on performance. All right, so we think about them in things like video games and, probably, very, very real-time applications. You maybe those little hoverboard things that, that's constantly updating, whether you're going to fall over and that kind of stuff. You maybe don't want that going through an interpreter. You probably want that to be as fast as possible Same thing with like missile launching and stuff like that. Okay, so these are things that need to be absolutely as close to real time as possible, where maybe the difference between 3 nanoseconds and 9 nanoseconds means something. All right, so that's when you would definitely choose a compiled language for that type of problem. Similarly, you might look at compiled languages maybe on mobile devices, okay, because you're already kind of underpowering the device. You know, your iPhone or your Android phone might have the latest, greatest mobile processor in it, but it's still not going to be the same processor that's in your laptop. Okay, so it's a lower power processor. It's running off a battery rather than wall power, so it's already having to internally make some decisions that might further slow its performance. So you aren't able to rely on the fact that, you know, it's going to be able to keep up with everything. So typically the languages we write our mobile applications with are compiled languages. Okay, but anymore, the processors inside of our phones have gotten so fast that it probably could be written in an interpreted language now, and we probably wouldn't notice. All right, so some of that's just left over from we're programming Android apps in Java, which is the same language we programmed Android apps in a decade ago. That's the way it works. Okay? All right, so that's kind of what that picture looks like. Pick your poison here in the middle, depending on which high-level language you're using. This will have an impact on performance, but most of the time, a human being's not going to notice. All right? All right, so we talked about this. 2 types of programming languages. We have domain-specific languages, and we have general-purpose languages. When we think about programming, we think about coding, almost all the time we're talking about general-purpose languages. That is a programming language that is built to solve the generalistic problem that computers are capable of solving. So most languages you've heard of are all general-purpose languages. Python, C++, Java, C#. These guys are all languages for solving any sort of problem a computer can solve. Now, every now and then, though, you'll have a language, very small language usually, that is a domain-specific language. And this kind of language, you know, you might have like the programming language for a washing machine or something like that, you know, where the Maytag guy comes out and he's fixing your machine, and, you know, maybe there's some sort of software patch or something like that, you know, the little tiny language for that literally governs like the difference between putting soap into your clothes and now it's the spin cycle thing. Okay, very small number of magic tricks that guy is doing. So the language for that is going to be a significantly simpler language because it doesn't have to do as many things. Make sense? So those would be domain-specific languages. Programming is programming. They're just going to have way less flexibility for solving. You know, you're probably not going to use the Maytag washing machine language for writing an operating system. Probably, I say. There's probably some competition out there where, you know, that's something that you could probably do. There is I think it still goes on, but there's a programming competition where who can write the longest one-line program that does something. And that'll make some sense to you when we start actually writing code, because you can kind of string lines of code together. It doesn't work well with Python, but like a language like C++ or C, where you can really put everything on one line, but then it becomes a lot more difficult for a human being to keep up with it when you have, you know, 7,000 what should be lines of code all on one big long line just right next to each other. It's really hard to sit there and write that. But, you know, I think one year somebody wrote the whole game Pac-Man or something like that in one line, and, you know, that kind of stuff. Just more of, you know, it's like parlor trick type stuff. Not really important from a programming skill set perspective. All right, so generally when we're talking about programming, we are talking about general purpose languages, but do know that there are some programming languages out there that exist for solving very, very, very specific tasks. Actually, a really good example of that is actually really big in industry is CNC machines. There's a programming language for programming CNC machines, the things that are built for like making tool dies and things like that. That's a very specific, domain-specific language for that actually pays really, really well. And they're pretty often looking for CNC programmers because the people that learned CNC programming as a skill set in some sort of trade school a long, long time ago, they're now retiring. So they have to turn to the younger generation that probably did not learn CNC programming, but are computer programmers who could now pick up CNC programming fairly quickly. So it actually can be fairly lucrative. Okay, but you'll be going into some shop where you have the whole bunch of the brawny guys with 50 different knuckle injuries and stuff like that, and you're got the soft hands. It's like, look, I've only been away from a keyboard for 5 minutes, but you get all this protective equipment on. But it can pay really, really well. Okay, now 3 kinds of programming languages. We have functional, we have procedural, and we have object-oriented. Now I'm going to purposely not talk about functional. When you take the 470 class with me, we're going to write our own programming language in there, and we're going to be using a functional programming language. It'll make a lot more sense to talk about that then. But if the 10-second version of this, if you have one of those TI Texas Instrument graphing calculators, and there's a programming language for that, that's a functional language, a language that happens in terms of functions linking to other functions, linking to other functions. And it's usually kind of a list-based language. So that's all I'll say on that. I won't ask you questions about functional languages in here. Okay? But procedural versus object-oriented, that's a really important concept. And it's even more important for us in here because technically most of the languages we're going to be learning modernly are going to be object-oriented languages. Python, for example, is an object-oriented language. But for most of the first half of the class, let's say, we're going to be using this object-oriented language, Python, in a procedural type of way because we're going to be kind of learning the basics, right? So we're actually going to be writing procedural programs using an object-oriented language. So let's talk about what the difference is. The high level of this is a procedural language tends to be this monolithic thing with a zillion lines of code, and you see all the details and things like that, where an object-oriented language gives you, tools for making things look a lot cleaner. All right, but let me give you a real-life example of this. Let's say that we have the procedural version of a telephone. All right, so up here on this desk, let's say you walk into the class, and I just have this giant pile of wires up here. All right, and I say, this is a telephone. And, first, it's like, okay, it's just a pile of wires. But then you come up, you do some investigation, you find the headsets, you find some buttons and things like that, and you fish through all the wires, you hear the dial tone as if that even exists anymore. But you're ultimately convinced that that is a telephone, right? Even though visually it looks like a pile of wires. Now, when you go back to your dorm room, you go home and you have your telephone that's still connected to a landline, again, as if people still do that. We're all convinced that inside that plastic container, there's a whole bunch of wires and crap, right? We believe that. And we know if we really, really, really had to get to those wires and circuit boards and all that stuff, we could, right? There might be a couple of screws. Otherwise, you just pry the thing open with your duct tape screwdriver monstrosity. Okay? But we believe it's in there. But we know when we use a telephone, we don't need access to those wires. We only need certain parts. Okay? The procedural version of a telephone would be that pile of wires that we know is a telephone, and when we go to use it, we have to kind of fish through the details to get to the headset and get to the buttons and make our phone calls. So we're only using 2 or 3 parts of it, yet we're having to fish through all the details in order to actually utilize it, right? The object-oriented version of a telephone, we start with that same pile of wires. We get a nice little container, all right? That's our object, okay? Most of our modern-day object-oriented languages, that's called a class. So object-oriented languages give you this little Tupperware container called a class that you shove all those wires into and stick the lid on it. So now everything's inside this bucket. This is my telephone, but wait a minute, I can't use it, right? Because I need a couple of things that are in there. I need the headset and the buttons and that kind of stuff. So we poke a couple holes in the side of it. We stick those pieces out. Now it's a telephone, okay? So with an object-oriented language, only the public interfaces, the parts of that program, the parts of the details that we actually need to interact with are exposed. Everything else is hidden inside that container. We can get to it if we want to. We can pry it open and start making changes and stuff like that. But in terms of using that telephone, we all like to carry around our cell phone rather than have a dedicated backpack for all the wires. Make sense? Because 99.99% of the time, we don't need to access those wires. Okay? And for most of us, if we have a problem with our cell phone, we don't crack the thing open and start soldering stuff. Some of us do. Okay? But for most of us, we don't do that. We go to the cell phone store and we say there's something wrong with my phone, and even the people at the store don't do that. They just take it in and, they warranty it or whatever it is and give you a new phone. It's that kind of stuff. Okay? But for those of you who ever cracked your screen on your phone, you take it into one of those shops that'll replace the screen. They'll take a half hour. They pop it open. They take the old screen out. They have to hook it up to the circuit board that's in there. They have to replace a couple things. They crack it back together. But at the end of the day, they actually did have to get into those details to make a repair. But then when they hand it back to you, you have a new sealed phone that doesn't have that problem anymore. Make sense? All right, so we can get at the details, but they're hidden from us without some extra work. That's the difference between a procedural language and an object-oriented language, is a piece of Tupperware. That's it. Okay? Textbooks and things like that will try to draw it out in this really technical example, but there's no difference beyond that. In the 470 class, when we write languages, we'll write a procedural language, then we'll convert that language to an object-oriented language, and you'll see that the difference is almost negligible. It's one little thing, and all of a sudden the language is an object-oriented language. Okay? Modernly, this kind of goes along with just human nature to begin with. Remember, the job of our programming languages is to allow us to solve problems in a similar way to how we solve them in real life. Okay? Now, some of us are slobs, right? And we have messes around the house and things like that. And we're perfectly happy just letting those piles exist, right? Okay? But generally, we like to have nice little containers, organizational buckets where we can shove some of those messes. There's still messes inside of those containers, right? Okay, but we put the nice little lid on it and put a piece of tape that says this is stuff I'll never look at again. And then we unearth it 15 years later. That kind of stuff. But in real life, that's how we solve problems, right? Rather than having the pile that's sitting there with just a bunch of stuff, we shove it into a container, label the container, and if we need to get to it later on, we take the lid off, right? That's how we solve problems in real life. That's an ability that object-oriented languages give us. It's an organizational tool. Make sense? Okay. Two types of programming languages. We have loosely typed languages and we have strongly typed languages. Now this comes down to, remember we talked about the three ways that human beings solve problems? We remember things, we ask questions, and we do repetition, right? We're going to be starting to focus, starting today and into Friday, on that remembering things stuff, variables. And you've already been looking at those in the textbook, right? All right, so when we talk about loosely typed versus strongly typed, what we're really talking about is variables. So what you've learned in the textbook is that a variable is a name-value pair. Okay, it's a little container that we give a name to and we can stick a value in it. Okay? Loosely typed languages allow us to have a generic container that we can put whatever we want into it. Strongly typed languages require that when we create our container, we label it for the kind of value it's built to hold. Okay? So the real life example of this would be in a loosely typed language, you can go to Target, buy 3 Tupperware containers, and let's just say buy 1 Tupperware container, and you can put shoes in it, and then 2 weeks later you can decide that you're going to put tax documents in it instead. Okay? Because it's a generic container that could hold any kind of value. Loosely typed languages allow you to do that. Now, good programming practice actually kind of dissuades us from doing that. Usually when you're creating a variable to maybe hold your age, which is going to be a number, you don't want to then 5 minutes later put your first name in there, because chances are the variable's called age. And while a loosely typed language would allow you to store your name inside of a variable called age, it doesn't make a whole lot of logical sense, right? Usually you want to name your variable something that's meaningful so that you can refer back to it later on. You know, when you're remembering your phone number inside your head, even though you don't actually recognize that you're doing this, if somebody says, what's your phone number? There's this little tiny, lookup that's occurring in your brain, right? Where you're kind of like retrieving the information associated with your phone number, okay? Well, you don't go and look in the bucket that says shoe size, right? You look in the bucket in your brain that says phone number, right? So real life, we wouldn't put stuff in the wrong box if we're trying to do it right, even though sometimes we just do it out of convenience, right? Or put a new piece of tape on it and label the box as something else. But in a loosely typed language, the buckets that we create for variables are generic, and we can put multiple types of values in them. Strongly typed language, the real life example would be, we went to Target, we bought that Tupperware container, we labeled it to hold shoes. A week later, we decide, you know what, I really want to hold tax documents in there. They won't fit. Unfortunately, we keep throwing the documents in there, it spits it back out at us. We have to go back to Target. We have to buy the bucket that looks just like the old bucket, except this one's built for holding tax documents. All right, so strongly typed languages require us to identify the kind of value that a bucket is built for holding. Now, this has some consequences to it. In a loosely typed language, these guys are relatively slow. Very, 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 very similar to interpreted languages. In fact, you will find that, I can't even come up with an example where it's not the case, but let's just say nearly all loosely typed languages are also interpreted languages. Similarly, nearly all strongly typed languages are also compiled languages. All right, so loosely typed means it has to be relatively slow because we need this thing called the type inference engine, which kind of peeks inside the container before it allows you to do logic with it. So for instance, if you're trying to add 5 to your age, and you have a variable called age, just because it's called age doesn't mean there's really a number in there. The type inference engine is going to peek inside that variable and make sure that whatever is inside there is mathable. Okay, it can do addition and stuff like that with it. Because in a loosely typed language, you can certainly put your first name in there, and all of a sudden it's Mike plus 5, and like, okay, well, what does this mean? All right, doesn't make a whole lot of sense. So a type inference engine does some of that peeking for you. Again, this is extra layers of stuff that has to happen, which leads to it being relatively slow. That makes sense? All right, even though our modern computers are very, very, very fast, so who cares if it has to do some extra work? And 99% of the time, that's a safe enough assumption. Okay, almost always we're not going to notice a speed difference. Okay, but it is technically having to do some extra work. And that loosely typed caveat has to do with the nature of writing an interpreter. Okay, one of the reasons interpreters are easier to write is we don't have to do all this extra checking prior to runtime to find out what kind of value something was actually defined to write. But that then also means that during runtime, we have to be able to kind of roll with the punches. We can't rely on what the programmer named their variables. We have to kind of peek inside the container and take a look before we start doing math operations on ice cream cones. All right, makes some sense? All right, so loosely typed languages happen to be interpreted languages. These guys are relatively slow. Don't view that as being a bad thing. It's just a thing. All right. Strongly typed languages tend to be compiled languages. These guys are relatively fast. Again, don't necessarily view that as being a very good thing. It's just a thing. All right. At the end of the day, you're going to use the right tool for the job, and most of the time our computers are fast enough where we're not going to know the difference anyways. Okay? So we definitely don't want to have the mindset that compiled languages are better than interpreted languages. For some things they are. For other things, they might be, we could say, overkill. Because a lot of times it is more convenient to sit down with an interpreted language and just start coding and get something done, and you're not going to notice a speed difference. than it is to get a whole environment set up with a compiler installed and all this stuff that technically produces a faster program that you will never appreciate. Make sense? All right, so we're just going to call them equivalents. This semester you'll be using an interpreted language. Next semester we switch over to Java, and Android programming you'll be using a compiled language. Then you'll be doing Visual Studio and C#, which is also a compiled language, and then you will do Scheme, which is a functional language, also an interpreted language in the 470 class. You'll do C++ in the 450 class. You're going to be exposed to lots and lots and lots and lots and lots of different technologies. All right. So, where does Python fit in this big world? It's a high-level language. Okay, that's good. That's the human power tool. So we're going to say that if we can help it, unless we have a really, really, really good reason, we want to write stuff in high-level code. Because we like power tools, huh? Yeah. All right. It's an object-oriented language. It's a fairly new language. All of our modern languages tend to be object-oriented languages. It sounds newfangled or whatever, even though it's been out for a long time. This is not that big of a deal. All of our modern languages are object-oriented. It just says it comes with its own Tupperware containers. All right? It's a loosely typed language. So right off the bat, that tells us that Python is relatively slow, but who cares? It's a general purpose language. So Python can be used to solve all sorts of problems that we can ask a computer to solve. And it's an interpreted language, which goes hand in hand with the loosely typed language. So again, it's relatively slow, but who cares? Make sense? So that's where Python fits in the world of languages. If we were talking about C++ here, every one of these things would be the same, except loosely typed would be strongly typed and interpreted would be compiled. All the other pieces are the same. All right? All right, so now we go back to that idea of how do human beings solve problems? We remember things, we ask questions, and repetition. So kind of our first construct we think of with our programming languages is that mapping, that our way, the way for a computer programming language to emulate the way that we remember things is through something called a variable. Okay? And a variable is a name-value pair that we store somewhere in the computer's memory. Now we want to have some sort of understanding of what that ultimately means. Okay, so we're going to look at a list of primitive types. Now this is actually something that came from the C programming language. All right, this idea of primitive types. And most of our modern languages actually came from C. Okay, so that's why I say programming is a skill set and it doesn't really matter what language you're working with. So if you're a Python programmer and you go over to become a Java programmer, you're going to see huge, huge, huge similarities between the two because most of their syntax was stolen from C. Okay, because that's just how our language has evolved. And we'll talk about that in a later slide here. But so I'm actually introducing the primitive types from the C programming language here, which pretty much hold true in all of our modern languages. All right, so for the first couple of minutes here, I want to talk about these first four. All right, so a byte is a signed whole number. Signed means it can hold positive and negative values. So this can hold like the number 5 or the number -7. A short is a signed whole number. It could also hold a 5 or a -7. An int is a signed whole number. It could also hold a 5 or a -7. A long is a signed whole number. It could also hold a 5 or a -7. Why do we need so many different ways of storing signed whole numbers? We're thinking about this in terms of a strongly typed language. In Python, being loosely typed, we wouldn't say, hey, you're a byte, or hey, you're a short, or hey, you're an int. We just let that type inference engine figure it out for us. But at the end of the day, we're throwing numbers into a container, and that number is going to be represented in some sort of way. Okay? Why is it that the C programming language, and it follows more modern languages, have so many different ways of storing the exact same kinds of values? How many of you have computers in here? Most of us, right? Okay. How many of you have at least 4 gigabytes of RAM in your computer? Okay, we're talking about the memory in the computer, not the hard drive. Your hard drive might be like a terabyte or something like that, or if it's one of the newer ones, it might be smaller than that, but faster with the solid state. So at least 4 gigabytes, how many? What about at least 8 gigabytes of memory? 16? 32? 64. All right, so we had a maximum amount of memory of 32 gigabytes. We had several who had 16, a bunch who had 8, and pretty much everybody had at least 4 gigabytes, right? So what does it mean for, what is a gigabyte? When I say a gigabyte, what does that ultimately mean? Just a fancy name that makes you know, like, well, actually, sometimes you hear them just say, I have 4 gigs, okay, which is actually really, really misleading. Go ahead.
1,000 bytes.
Okay, ish. It's actually 1,024 megabytes, which is 1,024 kilobytes, which is 1,024 bytes. All right, and I'll have a slide that talks about that. So we're talking about the high level right now. It's a lot of bytes. Okay, it's a lot of bytes. Now, how many of you have ever upgraded the memory in your computer? All right, so what did you go from like 4 gigabytes to 8 gigabytes? Something like that? How much did you spend? How much was so you got a 4 gigabyte stick? How much was a 4 gigabyte stick? Even if you pay retail, like at Best Buy or something, what's like 30, 40 bucks? Not expensive in the big scheme of things, right? You're doubling the memory in your computer. In 1996, so before most of you were things, I had a computer. It was a 486 DX2 66 megahertz processor. Slow compared to today's computers. And we had to wait for the chip to get released. That's how cutting edge this thing was. And that machine shipped with 8 megabytes of memory. Let me just, before we talk about the actual math of it, I'm just going to show you the number real quick. So I mentioned that gigabytes, 4 gigabytes is actually 4 times 1,024 megabytes. So for 30 bucks, you got 4,096 megabytes. If I divide that by 8, so your machine, your budget pleaser machine that came with 4 gigs of RAM has 512 times the memory that my bleeding edge computer came with in 1996. All right? Now you just told me you were able to double the memory in your computer for 30 bucks, right? It's cheap. Skip a couple of pizzas. Okay? I decided to double the memory in that computer. So I went out and got an 8 megabyte chip to give me 16 megabytes. How much do you think that chip cost? $150 bucks? Take bigger steps.
$500.
Even bigger. $1,000. Okay, now hold on. Hold on. This was after the price of memory had come down.
Wait, what?
Putting things in perspective for you here. If you have this many megabytes, all right, and so we have 4096, right? So $30 divided by 4096 costs us less than a penny per megabyte. Right? Less than a penny. We have to round up. Yet I paid $125 per megabyte after memory had gone down in price. Memory used to be really, really expensive. It used to be our bottleneck. So as a programmer back then, when we wrote our code, we had to be as careful with the amount of memory we had as possible because we would run out. Famous guy once said that you never need more than 32K of memory. Anybody know who that is? Microsoft guy, Bill Gates. Okay. Now we have toasters with more than 32K of memory in it. You know, because it's got to make sure you could put your Spock or your Yoda on your toast, right? You know, you seen those? You can get toasters that'll like print an image on your toast because you got to have that. You never know when you need your Yoda toast. All right, so, you know, punchline is that way back then, you're looking up the toasters? Yeah, they exist, right? Okay. Way back then, memory was so expensive that when you got a computer, you might have paid $5,000 for a computer that by today's standards, you wouldn't even say it had memory. Okay, you have dogs that can remember more stuff. Okay, not really, but we underappreciate memory now. You'll have a much better appreciation over the next couple of classes, and you'll hate math again. But also know that I love conversion questions, converting things between bases, so you better learn it quick, because I put it on every one of my tests for the next 4 years.
Oh, no.
Yeah, it's fun. It's so good. So in any case, back then, when the C language first came out in the late 1960s, memory was really, really, really expensive. So they gave us some tools that allowed us as the programmer to be very, very, very specific about how much space we want to take up. We want to monopolize to hold a certain value. Okay, notice here that a byte is actually an 8-bit value, whereas a short is a 16-bit value. It's going to take up twice the space to hold a short. So if you only needed to hold a small value, so when I say an 8-bit value, what I'm actually saying is it can hold plus or minus 2 to the 7th power. So in a byte, we can hold a range of values between negative 128 to positive 127. And next class, I'll show you how we came up with those numbers. But for right now, just that's the range of values, a fairly small range of values. But do you think when you're programming, it's fairly common that we just count from like 1 to 10? Or 1 to 100, something like that. So there's plenty of examples where we could fit our numbers inside of negative 128 to positive 127. A short can hold negative 32,768 to positive 32,767, right? We just quickly did the math of 2 to the 15th power. We could all do that in our heads? My precision goes down after this. So an int is a 32-bit number, plus or minus 2 to the 31st power. That's roughly negative 2.1 billion to positive 2.1 billion. And then a long is plus or minus 9 quintillion. It's a 64-bit number. Really big, okay? And if you need things that are even larger than that, because even though 9 quintillion seems really, really, really big, it's not infinite. So if you did need numbers bigger than that, you can move on to some other objects and stuff like that that let you have arbitrary size values. But the point here is that these guys exist because we needed them back in 1968 and 1978 and 1988 and 1998 when memory was still, by today's standards, expensive, right? As a programmer, it was up to us to be very good stewards of how much memory we had because we didn't have a whole lot of it and what we had was really expensive. Now you don't have enough memory, $30, you double it. And you got more than you ever need. So today's programmers, you'll never see somebody use a short today. A byte, you'll never see them use a byte for the size. Sometimes you'll see them use bytes for like video streaming or something like that, just because that happens to be the size that the data comes in as. It just has to be the right size bucket. Usually programmers today use an int, and if that isn't big enough, they use a long. We don't even care about the amount of memory we have. We have to 4 zillion ints. We got room. No problem. We don't even think about it. But back in the late 60s, we had to think about it. And we have things that are left over from those languages because our modern languages are based on those languages. Make sense? Questions, comments, concerns, bribes? You got a bribe? Go ahead.
So if you were, like, no homework, you can make a variable and integer, an int. Could you type in byte instead?
Not with Python. Yeah, and Python doesn't let you define types because Python's a loosely typed language. But if you were in Java or C# or something like that, you could say byte b equals 7. You could also say short b equals 7. You could say int b equals 7 because 7 would fit in any one of those. All right, pay attention to the Blackboard. I'll probably put up the next section. For reading, I'll probably just do one more section, so if you wanted to get ahead, you can. I just want to keep limping forward in the book until I finish catching up. All right? And I will see everybody on Friday.